Section 2.4 is on page 57, talks about exact equations. So what's an exact equation? That is, suppose that some m of x and y and some n of x and y are continuous. Their first partial derivative is continuous on some rectangle R. Then we say this equation, now notice the m is associated with the x and the n is associated with the y, the way they have it, is an exact equation in R if and only if the partial of m with respect to y equals the partial of n with respect to x, basically kind of backwards. And that holds for any x, y in that domain. Now, what's so important about exact equations? Definition 2, if the differential equation m times dx, n times dy is said to be exact in a rectangle R, if there is a function f such that when I take the partial of this f with respect to x, I'll get m, and when I take the partial with this f with respect to y, I'll get n. So basically, it's saying I could find f of x, y such that if I take the partial of f with respect to x, I will get that piece, and if I take the partial with respect to y, I'll get that piece. Now, for those of you that took differential equations, for those of you that took linear algebra, this is more like and if you really think about it, that's more like okay. So we take the partial of m, and m is the quantity that's being differentiated with respect to x, plus, and we take the partial with respect to y of the quantity that's being multiplied by dy, and we see if they're equal, we say that's exact. Another way of doing this, we call that the del operator is the partial with respect to x, the partial with respect to y. So if we take del and you cross it with f, where f is m plus n, in that order, then excuse me, the partial with respect to x, the determinant of this, if that equals 0, then f is exact, which is identical to what they're saying, because if these are equal, if you subtract them, you should get a 0. And that's really what you're doing here. So this is another way of doing this. If you want to do that, you can. It's up to you. So I'm going to do both on a couple of those. Probably I'll stick with the traditional. So this is dx, this is m, and this is n. So if I take the partial with respect to y of m, I should write it out. I will start taking the derivative right away. That would be a 2y negative. That will be a negative 2, I'm sorry. And if you take the partial with respect to x of x, that would be 1. Since those are not equal, you know automatically this is not exact. So classify the equation as separable, linear, exact, or nonetheless. This is not exact. Separable, I can't separate the y, so it's not separable. And linear, that's not going to work, because if I say dy dx, let me think. Could that be linear? Dy dx plus, if I divide by x, that's allowed, that's y over x. I can see that this is linear because if I solve for dy dx, divide by x, so that will be minus 2 over x times y equaling negative 10. If I divide by x, that's 7/3. So that is linear. So this is linear. It's not exact and it's not separable. All right. Now, let's get to the next problem, number 4. So if I apply what I just did, del crossed with f, assuming this is f, so if I take the partial with respect to x, the partial with respect to y, and the I component is really y e to the xy plus 2x, and the j component is x e to the xy minus 2y, I could say that is the partial with respect to x, the product rule, 1 times e to the xy plus x derivative of e to the xy e to the xy times y, minus the partial with respect to y, product rule, 1 times e to the xy plus y times derivative of e to the xy is x e to the xy, and if I subtract those I do get a 0, so yes, this is exact. So identically, if I take the partial of this with respect to y, the partial of this with respect to x, I'll notice they're exactly the same. Is it separable? That's not possible. Not separable. And is it linear? dy dx? Nope, you're going to end up dividing by a multiple of either. The product of those, there's no way you could shake it. So this is not linear. And if I run to the next problem, again, you could do this in real life. If I take the partial of this with respect to y, that's 2y. I take the partial with respect to x, that's a 0. That is simply 2y. So yes, this is exact. That's 1. Is it linear? Let's see, dy dx. Okay, I can try dy dx first. If I divide, you're looking at dy dx equaling, so this is gone, negative y squared over 2xy. Nope, that's not going to work for y. Does it work for x? Can you go the other way around? Divide by the y both sides. So y squared dx dy. Yeah, that might work. So if I divide by y squared dx dy plus cosine, no, plus 2y over y, of course that reduces, equal negative cosine of y over y squared. So yes, we say this is linear, but where the independent is y and the dependent is x. And is it separable? No, not separable. And if I look at the next problem, if I take the partial with respect to theta, that is 1. And if I take the partial with respect to r, so this is not exact. Separable? No, I can't separate those for sure. But if I divide by, again, if I divide by the theta dr, that wouldn't work. But if I divide the other way around, if I divide by theta both sides, so I'm looking at dr d theta, and divide by theta each of those, plus 3 over theta r, and move that to the right side, theta plus 1, right? This is a function of theta. This is a function of theta. Yes, this is linear. Again, with respect to theta being independent, r being dependent. So it's important to classify those to know when can you solve them and when can't you. Now, what's the big fuzz about this exact? Determine whether this equation is exact. If it is, solve it. From what I saw, I think the majority of what they give us are exact. So again, you could do this really quickly. You could do del crossed with f if you wish. So where del is the partial with respect to x, the partial with respect to y, that's the same as the calculus operator. This is 2x plus y, this is x minus y minus 2y. So the partial with respect to x is 1, the partial with respect to y. So yes, if it is, then this is what you're saying. You're saying if it is exact, that means I can find a function f where if I take the partial of f with respect to x, I'll get m, which is this. And if I take the partial of f with respect to y, I will get n, which is this. So you start backwards. Basically what you want to find this vector field, that's what they call it. You want to find this function, we call it function f, such that when I take the partial of f with respect to x, I get this. So that's where we start. And we integrate. Now we're undoing a partial derivative with respect to x, right? So this is kind of like a partial with respect to x, like a dx, but really dx. So you would say this f must be with respect to x, that is x squared plus xy, because that's considered a constant, plus, now comes the tricky part, a function of y. Why is that? Because if f was x squared plus xy plus 5, the partial of f with respect to x is going to be 2x plus y plus 0. And if this function was x squared plus 5y plus xy plus 5 plus y to the 50th power, the partial of this with respect to x is going to be 2x, a y, and this is going to be a 0. So when you're going back, this is sort of like the plus c that we're used to, but in this case, since when you take a partial with respect to y, you ignore all the y's, you're gonna, with respect to x, you ignore all the y's, you have to take that into account. And now just to find c, guess what? It's really simple. You're gonna use the second half. Well, how we're gonna use the second half? This is what we're gonna say. We're gonna say, look, if I take the partial of this answer with respect to y, that's 0, that is x, plus g prime of y. That must equal that component. So the x's cancel out, and if g prime of y equal negative 2y, whether you integrate here with partial or none, since it is only a function of y, g of y would be y squared. So replace this by y squared, and that's my f. Now there should be a constant in there, of course, but this is how they write the answer. Okay, you know I'm supposed to write y squared, right? And now, guess what? Take a partial of this with respect to x, you get 2x plus y, there it is. Take a partial of this with respect to y, oh my god, that was a negative, right? Would you look at that? Okay, you guys gotta be careful not to make these mistakes. If you take a partial of this with respect to y, that will be x minus 2y, and there it is. So that's how we're gonna do every problem. If it's exact, then you could find a solution. And we write the solution that way because of linear algebra. So we're not going to get into that much. If you're not liking this del crossed with f, you really don't have to use it. Here, take a partial of this with respect to x, that with respect to y, I just think that's more work. So that would be negative cosine of x sine of y. And take the partial with respect to x of negative sine of xy minus 2y. that would be, oops, I'm sorry, I meant negative sine of x sine of y. Well, with respect to y, that's going to be, with respect to x, that's going to be cosine of x, and this is a constant, you just drag it with you, and that's a 0. Man, I'm making a massive mess here. So yes, it is exact. What does that mean? That means I'm going to find this f, well, they call it f of xy, right? Such that when I take the partial with respect to f, with respect to x, I'll get that piece. And when I take the partial with respect to y, I'll get that piece. Well, that's where we start. We say, okay, if that's the case, since this is exact, the partial of f, it doesn't matter where you start. I'm going to start with x. The partial of derivative of my answer is going to, with respect to x, is going to be the cosine of x, cosine of y, plus 2x. If I integrate, and I'm doing a partial derivative with respect to x, this is a constant. Cosine of y you leave alone. What do you take a derivative of to get that cosine of x, sine of x, cosine of y, plus x squared plus a function of y. Now just find the function of y and you're done, and that's where the second piece comes in. Two ends. One, if I take the partial of this answer of mine with respect to y, which is negative times a negative is a positive, sine of x, sine of y. That's a 0, plus g prime of y. I should get that component, and that component happened to be, let me see, what did I miss? Okay, so if I integrate, the integral of sine is cosine, right? Why am I having a hard? Let me see. If I integrate with respect to x, you take a derivative of sine, you get cosines, okay? And that should equal, okay, let me see what I'm doing wrong. Let me redo this, but I'm not sure what did I do wrong. So if I start the partial with respect to f, the partial of f with respect to x is going to get me the cosine of x cosine. Okay, so if I undo a partial derivative with respect to x, this f is going to happen. This is the sine of x. Derivative of sine is the cosine times cosine of y plus x squared over 2 plus a function of y. There we go. Now if I take the derivative of this, if I take the derivative of this with respect to y, derivative of cosine is negative the sine. Sine of x is a constant. Derivative of cosine is simply the sine of y plus g prime of y, and that should equal this piece, which is negative sine of x sine of y minus 2y. So those cancel out, so I'm left with g prime of y equaling negative 2y. So if I integrate with respect to y, since it's only in terms of one unknown, that is going to be negative y squared. So my final solution is f is sine of x cosine of y. Now when you're done with this, you could check your work really quickly, and again, they always set that equal to c. Now you're supposed to pick a constant there, but they set that equal to 0 every time. They call it k really, but it doesn't matter. So you could check every time, take a partial derivative of what you got with respect to x. You should get sort of like the I component right there, and take the partial derivative with respect to y. You should get that right there. So I did one of each on those. If I look at this problem, all right, well, take and notice this is a y and a t. So here I'm going to take the partial with respect to t of t over y. That is 1 over y. And if I take the partial with respect to y of 1 plus natural log of y, that's 1 over y. So this is exact. Again, they give us most of those exact. So I start off by saying, well, all right, then guess what? This should work. That is, I should take the partial of f with respect to y of t I should take the partial of respect to y of this function of mine, and I should get t over y, and I'm going to integrate. I'm doing a partial derivative with respect to y. So with respect to y, t is a constant that's natural log of absolute value of y plus a function of y plus a function of t. That is what f equals. Now if I take a partial of this with respect to t, that is if I take a partial of this with respect, so the partial of just rewrite it nicer. Here we go. The partial with respect to t, that will be a natural log of absolute value of y plus g prime of t, and that should equal 1 plus natural log of y, assuming that y is positive. We ignore the absolute values. So, and we integrate. G of t is simply t. So here we say this function of ours is t natural log of y plus t, and we're going to set that equal to k, where apply the gradient on that, and you will get the partial. You'll get exactly what they have. We're not going to go there because that's not needed yet. Now, what if they give us initial conditions? The same idea here. They say solve the initial value problem, and those are exact. You could check if you wish, but they are. So, if I start with the partial of this f with respect to x is really y e to the xy minus 1 over y. And if I integrate, I'm doing a partial derivative with respect to x. F would be, with respect to f, y is a constant. This is e to the xy divided by the constant, which is y. I love it when it does that. Minus, and the partial of, that's a 0. The partial with respect, I'm sorry, I'm doing that. That's 1 over y. So with respect to x, there it is. Plus a function of y. Now, if I take a partial of f with respect to y, I'm going to get, let's see, e to the xy times x minus x over y squared plus g prime of y. And that's going to equal x e to the xy plus x over y squared. Those cancel out. And let me just check. What did I miss? Negative xy, that is right. I messed up the derivative here. When I took a derivative of this, since that's y to the negative 1, that becomes a positive. Those cancel out. So g prime of y equal 0. And if you integrate, g of y is simply a constant. Call it k. So now my function is f equals e to the xy minus x over y plus some function k. Now if I take x and replace it by 1 and y by 1, so if I set this equal to C, like what I've been doing, then I know that when x equal 1, y equal 1, that's e to the 1 minus 1 over 1 equals c. So I could say e to the xy minus x over y equal e minus 1. There it is. That's the answer. And last problem. Again, I picked one of each to make sure that we touch on every aspect of integration you come across. This is also exact. The partial of this with respect to y is secant squared of y. And the partial of this with respect to x, since that's linear, it's secant squared of y. Again, you need to check those. If they say solve, these are exact in this section. They get to be all exact. So if I say the partial of f with respect to x is tangent of y minus 2. And I'm undoing a partial derivative with respect to x. I will say f is derivative of tangent of y is a constant, so that's x tangent of y minus 2x plus g of y. Now, if I take a partial of this with respect to y, that is x secant squared of y with respect to y plus g prime of y. And that's going to equal x secant squared of y plus 1 over y, because it must equal that. And those drop off, and if I integrate, I'm getting g of y to be natural log of y. And since y is positive, I could ignore the absolute value, so that's natural log of y. So I could say x tangent of y minus 2x plus natural log of y equals c. Now, when x equals 0, that's a 0, that's a 0, that's a 1, but natural log of 1 is a 0, so c is 0. So I could say x tan of y minus 2x plus natural log of y equals 0 is the specific solution for this problem. And that's pretty much it for this section.